We just took a systems level view on data development with staff research scientist Chris Glaze. And now we're going to hear a talk titled Skillet, a data driven skills framework for understanding and training language models. Our speaker was a postdoctoral researcher at Stanford and received his PhD from UCLA. He is currently an assistant professor in the computer sciences department at the University of Wisconsin-Madison, and he's studying the foundations of data-driven systems and machine learning, with a focus on foundation models, auto ML, learning with limited data, and geometric ML. When our speaker is not pursuing his passion for ML, he is busy raising his 2-year-old twins. Love that fun fact. Please join me in welcoming Fred Sala to the stage. I hope you enjoy this talk.
Thank you so much, Rebecca, and thank you everyone for joining us. My name is Fred Sala. I'm an assistant professor at the University of Wisconsin-Madison, and today I'll be talking about Skillet, which is a data-driven approach for understanding and for training language models. So let's jump right into it. This is joint work with folks in my group at Wisconsin, and also with Chris Ray's lab at Stanford, with Mei as lead author. And this is work that was presented at NeurIPS as a spotlight just a month ago. So in addition to this work, I'll be talking as a bonus about some recent work that we've just had accepted at iClear about robustifying zero-shot models. And it'll turn out that these two things are very closely related. So let me go ahead and start with Skillet. Our basic motivation is actually really simple. As all of you know, large language models can do a ton of different diverse things. They can write code, and that's a very popular use of them. Of course, they can chat with users, which is how they became so prominent in the first place. And they're also capable of doing cool things like generating creative content. Now, all of these things are basically a function of all of this huge amounts of data that they've seen during training, and different kinds of data contribute to different capabilities that these models have. So a natural question for us to ask is, how do we select data to help these models be able to do all of these different diverse things? And specifically, what's the relationship between some particular data component and all of these different capabilities that we mentioned? Now, this is a pretty tough question. So we need some inspiration out there to try to figure out how we can try to understand it. And a natural place to look for inspiration is from the way that humans actually learn. Now, humans and large language models are not exactly the same kind of thing, but we can still come up with ideas by looking at very simple notions of learning for humans. For one, humans tend to learn skills in a particular order. So here's a really, really simple example. If we're learning math, we start out with some basic skills like addition, subtraction, and then we go from there to more complicated skills like multiplication, division, and so forth. And then finally, we learn very complex skills like algebra, for example. And this builds on all these simpler skills that we learned first. So a natural question for us to ask is, do language models also learn in this way, where they learn simple skills first, and then this contributes to learning more advanced, more complex skills as they go on? So the cool thing here is that we found that indeed this is actually the case. There in fact do exist sets of skills that can be learned more efficiently in a particular order, just like how simpler skills to more complex skills was the right order for humans. And even better, this is not just something that exists out there. It's not just a diagnostic about how large language models learn. It's something that we can in particular exploit. In other words, we can figure out how exactly to choose training data to show the model to get it to learn capabilities in the most efficient way possible. Let's figure out how this works. The first question, of course, is, can we come up with a meaningful definition of what a skill is? So for this talk, we're going to do something very simple. We're just going to say that a certain capability, a certain behavior that the model can do that gets associated with some piece of data is a skill. And this is a very, very general definition. A task could be a skill. An entire data source could be a skill. A category or a family of tasks. All of these things could be skills. And we're going to think of our data set that we have access to as being partitioned into different groups that correspond to their particular skill. So in the simple toy example that we're showing in the diagram below, we have 4 different skills, and we can see all the data associated with those skills: S1, S2, S3, S4. Now, what do we mean by an order over skills? Recall from our inspiration with human learning that we were talking about simple skills and then more complex skills. In the particular case that we have here, we don't have such a natural or intuitive ordering. Instead, we're going to define one that's based on how well skills are learned. So let's go ahead and define what we call a skills graph that encodes this information. All of the nodes in this skills graph are just the different skills that we talked about. So we're going to have nodes for S1 through S4 in our little toy example. We're going to put an edge between a pair of skills if getting data from one helps us learn the other. So let's see what this means in the diagram on the right. So over there, we have two curves. We're measuring how well we perform on skill 4, which is S4. That's the y-axis, the validation loss on it. And then we have two curves. We can train on data associated with S4 by itself. That's the green curve on top. Or we can train on data that takes some samples from both S2 and S4. And in this case, it's a uniform mixture. So as we can see, even though both curves are going down, which means that our model is getting better at skill S4, the amount it goes down is better for this mixture of S2 and S4. In kind of intuitive terms, this means that S2 helps S4. It can be thought of as essentially the type of prerequisite. So in this case, we can put this directed edge from S2 to S4 in our graph. Okay, so now we have this kind of notion of a skills graph that encodes the information about how skills are learned. We now have a notion of ordered skill set, which is just this graph. Now, hopefully this graph is not a trivial one in the sense that it's not empty, in which case skills would be completely useless to one another, or complete as well. But anything beyond these trivial cases is a useful notion of an ordered skill set. So now let's see an example of this. Let's suppose that we're interested in question answering and question generation, which are two different tasks in both Spanish and English. The two combination of language and question generation or question answering gives us 4 total skills here. So here's the particular graph that we can find. If you look at the bottom, we have that Spanish question generation is actually helped by getting samples from all 3 other skills. And the thickness of these edges, it indicates basically how useful these things are. So it's not surprising that question answering in Spanish is really helpful to Spanish question generation, but even English question generation is helpful, and even English question answering as well. So let's see what this exactly means if we go back to one of the curves that we showed before. So here we're looking at the validation loss for Spanish question generation. And you can see the blue curve where we're training our model just on Spanish question generation data by itself. And indeed, initially, after a small number of steps, our validation loss does go down and the skill is being learned, but it kind of levels off after a certain point. On the other hand, if we're going to take uniform samples from all 4 of these skills, then we have this orange curve that goes down at a much faster rate after the initial number of steps. So in other words, having this mixture with all of these other skills, it helps us learn a particular capability much more efficiently. Okay, so what can we do with this observation? So far, we can't actually take advantage of it. It's just a question of how things behave when we have some particular mixture of data in our data sets. The next bit that we're going to talk about is how to actually take advantage of this, essentially use a new algorithm for data selection to train these capabilities as efficiently as we can. So the problem setup is the following. We're going to have a pre-trained language model. We're going to continue training this language model or potentially fine-tuning it. And we have 2 sources of data. One is a set of skills called the training skills. And we have a bunch of data X-train associated with these. You can see it on the left. We also have a set of evaluation skills and a bunch of data associated with this. And that's this middle block here. Now, these 2 things may be disjoint potentially. We could have different skills in training and different skills in evaluation, or they could potentially overlap. This gives us a lot of flexibility. What it basically means is that we can both just do training, or we can do things like fine-tuning, or even kind of auto-distribution targets for new skills that we can't directly train on. Now, our basic setup here says that we would like to take n samples from our training set, place them in some particular order to show to the model for training, and we want to do this in a way that we can perform as well as we can on the evaluation set X-eval. Okay, so here's our basic algorithm for doing this. It's actually going to be extremely simple. We're going to make this into an online problem. We'll take our training procedure, split it into T rounds, And then at each of these rounds, we're going to go ahead and adjust a mixture of skills. In other words, we're going to have a different proportion of data from each skill for each round. Okay, so the first step is to get access to our skills graph. We're not going to discuss right now how we can actually do this, but if you're interested, you can check out our paper. The next step is we're going to start out with some initial data mixture P1. In our little toy example with 4 skills, we have this uniform mixture with 25% from each of these different skills. Our next step then is to train the model for 1 round using this initial data mixture P1. And from doing this, we get some updated model F1. Then the interesting step, and the only non-trivial step here, is that we're going to construct a new mixture, P2, that's going to be done from some update rule that I'll discuss in a second. So notice that in our toy example here, skill 2 now has a lot more data for it, 38% of the mixture, and skill 4 has been kind of deprioritized. It's now down to 14%. So we're going to repeat this process. At each round, we're going to go ahead and kind of adjust our data mixture. We're going to use that for training our model. We're going to construct a new data mixture and repeat this whole process. The next kind of interesting question here is how exactly should we modify this data mixture? And you can already tell that we're going to have certain ingredients here, one of which is going to be the skills graph that encodes this information about how useful skills are to learning each other. Here's the basic formula for this update rule that I've mentioned. And you can see here that we're at round T, and we'd like to adjust it for the mixture at round T plus 1. And the way we're going to do that is we're going to take our proportion at time T and multiply it by a factor. I won't describe each part of this factor in detail, but I will mention 2 things that are really critical here. The first is AIJ here, and this is basically just the adjacency graph entry from the skills graph. And really what it says here is how much weight on S train I is there, which is one of our training skill, based on how much it influences this evaluation skill J. And we're going to go over all M of these evaluation skills. So this is natural. We're just using this information that we got from our skills graph, which basically tells us what the ordering should be. The next component here is this loss, the evaluation loss for J. And really what this is saying is how easy is it to learn this particular evaluation skill? So we want both these factors because a particular model may be better at learning one skill than another. And the combination of these 2 factors is really all the information that we're using. Just a skills graph, which is fixed, and this evaluation loss, which tells us how well we're doing at learning the particular skill that we're looking at here. And we apply this rule again and again. It's simple and computationally efficient. And by doing this, we modify these mixtures. And this is really the entire algorithm for Skillet. Okay, so the next question is, how well does Skillet do? I'm going to show some results. This is just the example that we saw before with Spanish question generation. The blue curve is the one that we saw training only on Spanish question generation. Then we have the stratified example where we don't continue updating all of our mixtures. And then finally, Skillet, just the algorithm I showed, is the green curve, which performs best. And this isn't just for one limited example. We can do this for a whole bunch of different examples. You don't have to look too carefully at all these combinations of different out-of-domain tasks here. But basically, on 12 different baselines, 11 out of 12 Skillet performs best. And it often performs much better for a particular budget. So hopefully I've convinced you that Skillet is a really powerful algorithm. There's a lot more in the paper. We talk about how to efficiently learn this skills graph, which is a component of our algorithm. We talk about how we can discover in an unsupervised way different skills. Recall that these skills were just kind of behaviors that we could specify that were associated with pieces of data, but we are definitely interested in how to just discover these rather than specify them. And finally, we have a lot more experimental results, including synthetics, a bunch of real data sets, and even kind of a medium-sized model that we trained, a 3 billion parameter model that was trained on the red pajama dataset. Okay, so this was Skillet, an approach to ordering your training data in a way that you can learn capabilities in your language model as efficiently as possible. I'm also going to briefly discuss kind of this other approach, which is very useful for when we don't have access to this kind of data. And we call this work zero-shot robustification of zero-shot models. Now, these zero-shot models, they're quite similar to language models, which you can prompt in a zero-shot way. They're a very powerful new paradigm, and they've also been very fun for users to play with. So I'm showing a very simple example here of ChatGPT. I've asked it to create a specification, some code, and this kind of famous graphics package called TIX, which uses the LaTeX typesetting language. And essentially, I've just asked it to provide code for a diagram of a robot. And as you can see, I've gotten this code from it. I go ahead and compile it, and it produced this cute little picture of a robot. So this is something very cool. These models, without actually being trained at all, just using their pre-training capabilities, can go ahead and just be prompted or queried to do a whole bunch of different things. Unfortunately, there's kind of a downside to this. Because they've inherited all their capabilities from pre-training, you have all kinds of weird quirks that take place in these models. So let me show a visual example with a model like Clip. So in this case, I'm interested in predicting whether or not there's a pacifier in an image. And we can see on the left over there, we have an image of a baby holding a pacifier. And indeed, the prediction is that there is the presence of a pacifier. So the model got it right. However, if we look carefully, we can see that from this heat map indicating what the model's looking at and what it's using to make these predictions, it actually did not discover the pacifier. Instead, it looked at the baby here. Now, it turned out that this was okay because babies and pacifiers are very heavily correlated. So if I ask for a pacifier, very often the presence of a baby in the image indicates that there is a pacifier as well. Unfortunately, that's not always true. And if we look at the image on the right, with this piglet that does have a pacifier in its mouth, there's no baby to look at here. So the model instead focuses on other things. It says that there is no pacifier here. There are other things like a bottle. So basically, it gets it wrong. And this is an example of what's called a spurious correlation. So this is kind of an interesting question. Can we do something about these spurious correlations? Can we make these kinds of models more robust, whether they're language models or other large pre-trained models? Now, thinking about something like Skillet, if we have access to additional data, especially from a data set that distinguishes between these different cases with pacifiers, then we could use an approach like Skillet to very efficiently become good at these kinds of tasks. Sometimes, however, we don't have access to this kind of data or to enough quantities of it, and we have to do something different. And I'll very briefly describe kind of how we could do something like this. Well, one idea and one intuition that we might have is that many of these models, like large language models, they might actually know a great deal about these useful concepts that we're talking about. They might know a great deal about when pacifiers are there and when they're not, but perhaps at prediction time, they're not capable of using all this knowledge. Think of a student that knows a great deal of, for example, math skills, but actually just uses the wrong ones when he's taking an exam. So let's see if this is plausible at all. I asked ChatGPT here as well, if I'm trying to detect images of pacifiers, which features should I look for? And interestingly, it actually tells me a lot of very useful information. It tells me particular shapes and sizes and colors and textures and things like that. And it even tells me that there's things that are spuriously correlated that I shouldn't be using. So for example, baby bottles, which is exactly what we saw before. So if somehow I could get my model to respect all of this knowledge that it actually has if I ask it the right way, then I could make these models much more robust. And this is at the heart of this kind of procedure that we introduced. And please see our paper with the link here on the left. What we do is a very simple two-stage process. First, we ask the language model for these insights. And then after we've asked the language model for it, we go ahead and embed them and modify the model's representations. And essentially all we're doing here is boosting some of the features that we know are useful because the language model has told us they are. And we're kind of getting rid of some of the features that we know are just spurious and that we should not be using. And this fairly simple procedure can actually dramatically increase the quality of these kinds of models, even without having any external data. So kind of recapping what we've talked about today, if we have access to our data sets and we want to continue training our models, we have Skillet, a powerful procedure for establishing the right order and mixture of data that we should show our models. In other cases, we'd like to make our models more robust, but unfortunately we don't have access to all of this data, in which case we have different procedures that we can use to extract meaningful insights from models and kind of use these in a data-free way to improve the robustness of these models. I'll stop here. Thank you so much for inviting me. And if you have additional questions, please reach out. Thank you.